Okay, so that's our lesson for today. Apply properties of rational exponents. Well, here's the thing. Now that we know that actually radicals can be expressed in rational exponent form, we can use the properties of exponents with those rational exponent forms. Now, the properties, when you apply the properties of exponents to rational exponents, you get the properties of rational exponents, but they're the same properties, right? There's nothing in this list that wasn't in when we did properties of exponents. It's actually one thing that's missing from this list that was in that list. We'll go through these, see if you can think of the one that's in the properties of exponents. But there's 7 of them, and we only have 6 here. Okay. So the only thing that's different about this slide from the one I showed before is their examples all involve rational exponents, but the properties are identical. Right? A to the m times a to the n, add the exponents. Right? A to the m raised to the n, multiply. Right? A to the ab in parentheses to the m means distribute the exponent. Right? You can see all their examples on the side there. I mean, what's going to make this more complicated? Well, if you have trouble adding fractions, okay, you're going to have trouble. Other than that, it's the same properties. Right? How do you get rid of a negative exponent? We did that in the homework already. Right? You flip it to the other side of the fraction. And when you divide, you subtract exponents. And if you have a quotient raised to a power, you can distribute that power. But all these are just examples that use fractions for exponents. But the properties are still all the same. What's the missing property? There was one more. Anna? The zero exponent, right? Because that's not a rational exponent. So anything to the 0 power is 1. That's not in this list. But everything else is in there. Right, so try to use those properties to simplify these. These are your U-tries, 4 U-tries right away. Okay, so on the first one, what should you have done with that 3 outside parentheses? You distribute it, right? Now, what you can't do, you can't at any point in here multiply 5 times 7. Right? The 5 and the 7 have different exponents. So there's no way you're going to be able to put those together. So this has to be 5 to the 1/3 to the 3rd, 7 to the 1/4 to the 3rd. Okay, and then we simplify. When we raise a power to a power, we multiply. So 1/3 times 3 is 1, so that's just 5. And 7 to the 1/4 to the 3rd, what's 1/4 times 3? 3/4. Done. Okay, what are the properties of exponents we're supposed to do? Say we're supposed to do with that one. Since the bases are the same, 2, then what do you do with the exponents? You add them up, right? So that's 2 to the 3/4 plus 1/2, which is 2 to the 5/4. Okay. What do the properties tell us that we have to do with the exponents? When you divide, you subtract the exponents, okay? What's the exponent in the numerator? There's a 1, right? So that has to be 3 to the 1 minus 1/4, which is 3 to the 3/4. Okay. Now, can I combine the 20 and the 5 in the last one? You can't, because they have the same exponent, right? If I write this like 20 over 5, and then outside parentheses I've got the 1/2. You know, usually when you have something like that, you use the property and you distribute the 1/2 to the numerator and denominator. Okay, so you can certainly go backwards on that, right? Since here it was distributed on the numerator and denominator, let's pull it outside parentheses. I still have all raised to the 3rd. So that's 4 to the 1/2 to the 3rd. And 4 to the 1/2 means the square root of 4, so that's 2. And 2 to the 3rd equals 8. Okay, here's properties of radicals. We used these before when we were solving by taking square roots in the quadratics chapter. We did with square roots. We were doing this. Okay, well now they're more general. It's not just square roots, but it's any kind of root. You know, any kind of root means nth roots. That's what the n stands for. Okay, so if you have a radical of a product, then you can make that the product of radicals. You could split it into its component factors and take 2 radicals. Sometimes that's helpful. Sometimes it's actually helpful to take 2 different radicals and multiply them together and have one big radical. So this is like both ways. It can go that way or it can go that way. Same thing goes for the quotient, right? The quotient of a the radical of a quotient, that's the nth root of a over b, equals the quotient of radicals, the nth root of a divided by the nth root of b. And sometimes, again, we'll want to take a bigger radical, split it up so we can simplify both numerator and denominator. And sometimes we'll want to go the opposite direction and take 2 different radicals and put them into one. Right? And both of those are, pretty much properties of exponents. This product property, that's what this is. That's a product property. This is a quotient property. Okay, so use these properties to simplify. So in the letter A, they're cube roots, right? Is 12, if you're taking the cube root of 12, is 12 a perfect cube? Does it have any factors that are perfect cubes? No, so that's not helpful. How about 18? Is it a perfect cube? Or does it have factors that are a perfect cube? The answer is no. So if I combine them into one radical, the cubed root of 12 times 18, well, that's the cubed root of 216, and that's a perfect cube. So it makes sense to combine the radicals into one, and then you can simplify. 6. Right? Same thing on the letter B. The 4th root of 80, 80 is not a perfect 4th power. Now, the truth is that it has a factor that is. We could have simplified it in a little bit different way. Certainly, 5 is not a perfect anything to the 4th. But if you put them together, right, 80 over 5, that's 16, and that's 2 to the 4th, right? 2 times 2 times 2 times 2, that's 16. So the 4th root of 16 is 2. Now, one thing that I haven't seen, and maybe I'm just missing it, but I've looked at it for a couple times in this book. But if you notice, we just took the 4th root of 16, and this is the book's answer right here. They didn't put plus or minus 2, even though it's an even root. So somewhere in here, we get to the point where we say, when you're presented with a radical, an even root radical, you assume that they mean the positive. So we're only using the 2 now, instead of putting plus or minus 2. And that'll continue on from now on. So try to simplify those 2. Okay, so if you have the product of radicals is the radical of the product, which is 27 times 3, which is 81. And the 4th root of 81 is, sorry, I started to write 5 because I'm thinking of the next problem. 3. Okay, this one, the quotient of radicals is the radical of the quotient. Right? The 3rd root of 125, which is 5. Okay, when it says that we should simplify a radical, and now we're going to get into where we're not just dealing with numbers anymore, that we've got variable expressions involved. The simplest form, if the index is n, then there shouldn't be any perfect nth powers inside the radical. Like if we were taking a cubed root, then you can't have like a factor inside, which is a perfect cube. You have to simplify that part of it. And the other thing is, if the denominator has a radical in it, you have to do something to rationalize the denominator. Right? We did this a little bit, when we were dealing with square roots. Now it's a little bit different when you're dealing with nth roots. But I don't think you'll find it that hard to figure out. So simplest form means there can't be anything that's left inside the radical that could be simplified a little bit more. Right, here's an example. You're taking the third root of 135. Okay, let's say you don't know your perfect cubes very well. So you say, is 135 a perfect cube? And the answer is no. Okay, then you say, does it have any factors that are perfect cubes? And the answer is yes, is 27. Okay, now if you don't know where those numbers come from, remember this way to use your calculator. If I want to find how I can simplify the cubed root of 135, right? Notice there on the first line, I go to y equals. On the first line, I put x to the third. Okay, that's going to give me in the first column all of the perfect cubes, so I can look for 135. On the second line, y2, it says 135 divided by x to the third. So in that column, we're going to see what you get when you divide 135 by the perfect cubes. And we're looking for one that divides evenly. So again, on y1, put x to the third. On y2, 135 divided by x to the third. And then go to the table of values, which is second graph. Right? You go down the y1 column and look for 135. And you don't see it. Right? You go from 125 to 216. So it's not in the perfect cube column. So at that point, in between 125 and 216, go over to the column on the right and then start looking for, go up and look for a non-decimal, right? Like the first thing, 1.08, it doesn't go in evenly. 2.1 doesn't go. Okay, there you go, 5. That's a non-decimal. So we can break this into 27 times 5. And the cubed root of 27 is, go all the way to the left, 3. So this is 3 times the cubed root of 5, which is what they got right there. So again, you look in the first column for your number. When you don't find it, go over to the right and work your way back up until you find the first non-decimal. Right? In this case, 3 times the cubed root of 5. Okay, adding and subtracting radicals, right? You can only add or subtract radicals if they are what we call like radicals, which is kind of a familiar word, right? Like terms, like radicals. So, like radicals have the same index and the same radicand, right? So if you look at letter A, the fourth root of 10 plus 7 times the fourth root of 10. Both of those are the same. They're like radicals because they're both fourth roots and they both have 10 inside. So now you combine them by combining the coefficients, just like you do like terms, right? If I had 1x to the fourth plus 7x to the fourth, I would add the 1 plus 7. I get 8x to the fourth. Okay, I've got 1 times the fourth root of 10 plus 7 times the fourth root of 10. So add the 1 plus 7. That's 8 times the fourth root of 10. And whatever you do, don't change the radical. If you add fourth roots to fourth roots, you don't get square roots. Right? 1 apple plus 7 apples equals 8 apples. Right? Doesn't change the apples. And now, notice in the letter B, okay, now they're using the rational exponent form, but it's still the same, right? The exponent is like the index of the radical. the base is like the radicand. So as long as those two are the same, and they're both 8 to the 1/5, then you combine them by combining the coefficients. 2 plus 10 equals 12. Now what you don't want to do is, like, let's say you get all the way through that problem and you're all the way to the end right here. Don't try to multiply 12 times 8. You can't do that because 12 is not being raised to the 1/5 power. Right? As soon as you did, if you wrote this like 96 to the 1/5, right? That's like saying 12 to the 1/5 times 8 to the 1/5, which is definitely not where you started, right? You didn't have 12 to the 1/5, you just had 12. So don't do this stuff right there. I warn you because I see it all the time. Okay? Now, this is the kind of problem that you're most likely to be challenged with, which is, as you look at that, it would appear these are not like radicals. The cube root of 54 and the cube root of 2 are not like radicals. But you can simplify the cube root of 54, right? 54 is not a perfect cube. Does it have any factors that are perfect cubes? And the answer is yes, it's 27 times 2. And 27 is a perfect cube. So now just follow their work going along to the right there. Right? So they've broken it into a cube root of 27 times the cube root of 2. The cube root of 27 is 3. So now as I look at that, those are like radicals. So you don't want to just look at it and right away on the left and say, well, I can't do those. Can't be added. You got to simplify. And then you can, they're like radicals, so it's 3 times the third root of 2 minus 1 times the third root of 2. So 3 minus 1 is 2 times the third root of 2. So try that one. See if you can figure out how to add those two. So are those like radicals? As written? No. Could you simplify the cube root of 40? How did you break down the 40 so that it could be simplified? The cube root of 8 times the cube root of 5. Good. Right. Make that the cube root of 8 times the cube root of 5. And what is the cube root of 8? 2. So that's 2 times the cube root of 5. So now we've got the cube root of 5 plus 2 times the cube root of 5. So how many cube roots of 5 do we have? 3. 1 plus 2, 3. Okay. Now that we get into where we've got variables inside, I mean, again, this one thing that I didn't see in the book where they kind of bring this out, but we assume that even radicals are positive. We're not doing the plus and the minus anymore. And since the thing that we might be pulling outside of the radical now is a variable, or could be a variable, you know, variables can have all kinds of values in there. They could be plus, they could be minus. So to make sure that it's not a minus, we have to use absolute value symbols. Okay, when the index is even, if you take the even root of, you know, the nth root of x to the n, when you pull that x out, you got to make sure that that's a positive. So, I mean, if you look at it like this, right, what if I had the fourth root of x, no, that's not right. I meant to say the square root. What if I have the square root of x to the fourth? How many x's come out? All right. That's like saying x squared squared. So the square root of a square is, right, you get x squared. Come in. So in this case, it was an even index. I took the square root, but what's outside is x squared. Do I need absolute value symbols? I mean, is it possible that x squared is negative? No, I mean, you square a negative, you get a positive. You square a positive, you get a positive. So in that case, you don't need absolute value. But if I'm taking the square root of x squared, right, I get x. If x happens to be negative, then I'm just saying the square root is negative. And they're saying we don't want that anymore. We're going to say, when you see an even radical, it's got to be positive. So to make sure that it is, use absolute value symbols. And that's what this is talking about. Now, a lot of times in the problems, in the directions of the problem, they say, assume all variables are positive. Okay, well, at that point, you don't need to worry about anything, right? If all the variables are positive, then absolute value doesn't do anything for you anyways. And you'll see that a lot. It'll say all variables are positive. Okay, so simplify the expression. The third root of 64y to the 6th. Well, this one works out pretty easily because 64 is a perfect cube. Y to the 6th, well, y to the 6th could be written like y squared to the third. That's what they've done going from here to here, right? They wrote the 64 as 4 to the third. Y to the 6th is y to the squared to the third. So when you take the cubed root of something that is being raised to the third power, then what you pull out is the base, right? So in this case, 4y squared. Now, that's not usually, I mean, there's nothing wrong with the way they show this here. And if you want to show your own work that way because you think it makes sense to you, that's fine. Usually, I break it up into the different factors. So this is the third root of 64 times the third root of y to the 6th. And the third root of 64 we know is 4. And then in order to know how many y's I'm going to take outside parentheses, I divide the exponent of 6 by the index of 3. So 6 divided by 3 is 2. So go ahead and try the number 10. This you try right there. All right, what's the cube root of 27? And then how many q's can you take out if it's the third root of q to the 9th? 9 divided by 3 is 3. Again, you could write it if you want. You could write it like q to the third, so that it's clear that you're taking the third root of something raised to the third power. And that'll tell you what comes out, right? But I usually don't. I just divide the exponent by the index. And that works pretty good. Although, you know, what you see here is that in every case here, it always divided evenly. So we got all the variables out. Well, that's not always going to be the case. And I don't know if it's the next slide or it's the one after, but okay, it's the one after. So now we're doing quotients. Right, the fourth root of m to the fourth over n to the eighth. So you notice right away, if I'm going to do that divide thing, 4 divided by 4 and 8 divided by 4, it goes evenly. So, I mean, this is going to be a very simple one. You know, they've taken the step and split it into the radical of a quotient into the quotient of radicals. But now 4 divided by 4 is 1. 8 divided by 4 is 2. Done. So you try the number 11 on the bottom. Shouldn't take you more than 30 seconds. Everybody get that? Right. 10 divided by 5 is 2. 5 divided by 5 is 1. So here's where it gets more difficult. Okay, just scanning across the radicand. Look at those exponents and the index. 8 divided by 5 doesn't go. 14 divided by 5 doesn't go. So what it means is that some of the variables are going to come out, but not all. So you've got to figure out what stays and what goes. And you could definitely see how they've done it there. Notice that they said, okay, 8 divided by 5, it doesn't go evenly. So let's break it down into 2 factors with a base of a, and then let's get the most simplification possible. So you say 8's not divisible by 5. What's the greatest number less than 8 that is divisible by 5? And you say 5, right? That's why you've got a to the 5th, a to the 3rd, right? Properties of exponents says 5 plus 3 is 8. That works. Okay, b to the 14th. 14 is not divisible by 5. What's the greatest number less than 14 that is divisible by 5? 10. That's why they've got b to the 10th, b to the 4th. Now c to the 5th, that works. 5 divided by 5, that goes. So then they've taken a step where they wrote 2 radicals. And in the first radical, they've got all those pieces that are actually going to simplify. A to the 5th, b to the 10th, c to the 5th. And then in the second radical, they've got all the things that are not going to simplify. You can't take the 5th root of 4. You can't take the 5th root of a to the 3rd or b to the 4th. So they're going to stay. Okay, then now we can simplify this by just doing the divide. Exponents by index. 5 divided by 5 makes a to the 1. 10 divided by 5 makes b squared. 5 divided by 5 makes c to the 1st. And again, notice that they had in their directions, assume all variables are positive. Okay. Okay, now this is where the rationalizing of the denominator comes into play. I mean, if you're looking at this radical of a quotient, x over y to the 8th, I mean, there's nothing you can do with an x. You know, just an x to the 1st is clearly not going to come out, no matter what you do. But if we were taking the cubed root of y to the 8th, some of that would simplify, right? Would all of it simplify? Could you get all those y's outside the radical? 3rd root of y to the 8th? No, you could get the y to the 6 times y squared, but you'd still have something left. So notice what they did to make this, to rationalize the denominator. They've multiplied by y divided by y inside the radical. You already had y to the 8th. Now you got y to the 9th in the denominator. And you can take the cubed root of y to the 9th. Okay, so you do. So after multiplying by y over y, simplifying, they break it into two radicals. The cubed root of xy, can't do anything with that. The cubed root of y to the 9th is y to the 3rd. Done. We were used to doing, when we were doing this a couple chapters ago, that you might have something like the square root of 2 in the denominator, and we were always just multiply by the square root of 2 times the square root of 2. Okay, well, it's a little more complicated now, right? If I had 1 over the cubed root of 2, I can't multiply by the cubed root of 2 over the cubed root of 2. That would give me the cubed root of 2 squared, and that doesn't simplify, right? I would have to multiply by the cubed root of 2 squared over the cubed root of 2 squared. Right? When I put that together, I'm going to get the cubed root of 2 to the 3rd. Right? And now the denominator simplifies. That's 2. So you got to think a little bit more than just multiply the top and bottom by the denominator. It doesn't work that way. Okay. Okay. Perform the indicated operation. Assume all variables are positive. So again, what's the operation going on here? Subtracting radicals. What has to be true in order to add or subtract radicals? They have to be, what's the word? Like radicals, right? They have to have the same index and the same radicand. If you look at these two radicals, they don't. So you got to simplify. And that's what they're doing. Right? The z to the 5th, right? This one radical right there could be written like the cubed root of 2. I'll do it like they did on the last side. Times z to the 3rd times z squared. I break that z to the 5th into z to the 3rd times z squared. Right? The cubed root of z to the 3rd is, right? What's the 3rd root of z to the 3rd? Z, right? That's where this z comes from, right there. And then the rest of it, 2z squared, has got to stay inside the radical. Right? This second one, okay, we've dealt with this already, right? The cubed root of 54z squared, well, the cubed root of 54, we did this one before. That was 3 times the cubed root of 2. Okay, so that's where this 3 comes from. It already had a z outside the radical, but didn't have that 3. And now what's left inside? 2z squared. So now we do have like radicals. So again, how do you subtract like radicals? By subtracting the coefficients. Right, there was a 12z in front of this one and a 3z here. 12z minus 3z is 9z. Okay. Again, we've got this statement again. Assume all the variables are positive. But again, because these are cubed roots, it doesn't really make a difference. Cubed roots can be negative. Now, on your u try right there, it's a square root, so now it makes a difference. So go ahead and try that one. And that's the last slide. Right? So you should have simplified the square root of w to the fifth. Right? 5 is not divisible by 2. So what's the greatest number less than 5 that is divisible by 2? 4. Right? So you needed to break it into a w to the fourth times w to the first. A lot of you hadn't gone all the way. You had like w to the third times w squared. Right? That's not enough. W to the fourth times w. Then when you simplify, the square root of 9 is 3. The square root of w to the fourth is w squared, and you're left with the square root of w. Right? On the second one, right, there was already one w on the outside. Okay, when you split that w to the third into w squared times w, you got the second w. So there's w squared times the square root of w. Okay, now subtract. What's 3w squared times the square root of w minus 1w squared times the square root of w? 2. That's it. So there you go.